and the Raspberry Pi server.
My name is Matthew Connor, and I worked on the motor controllers.
My name is Jack Chu, and I worked on the PIC32 and UART.
My name is Eric Cayetano, and I worked on the robot arm.
Our project models a delivery and unloading system in which a rover delivers a 1-inch block whilst navigating obstacles. Another rover waits to unload the delivery rover once it has navigated the course. Obstacles are detected by PIC32. An A-star pathfinding algorithm is run to determine the best path from the start to finish, and this path is sent to the delivery rover as a set of coordinates on the board. A servo-powered arm loads the delivery rover. All of the PIC32 microcontrollers communicate wirelessly to coordinate the steps of the system.
Our objective and specifications were to develop an automated package delivery model system with microcontroller boards that can communicate effectively. In addition, we were to develop a pathfinding algorithm that updates and compensates for obstacles that are randomly placed on the course. We also had to develop a process that the system will use to perform all of the actions in a logical order. Finally, we had to adapt to any necessary changes that the system undergoes throughout the development.
The process begins with PICam2 mounted over the board. The Pixicam interprets large blocks on the board as obstacles. Upon starting, the delivery rover requests the solution through the obstacles from the server. It is at this time the best path is calculated and sent over Wi-Fi to the delivery rover. The block's trip begins with a server-powered robot arm picking up the block and placing it on the delivery rover. When the arm completes loading, it updates the server to tell the delivery rover to begin navigation. The rover takes the best path as a set of XY coordinates. These coordinates are converted to instructions the motors understand in order to move from coordinate to coordinate. Once at the destination, the rover lines up and turns around into a position in which the unloading rover will remove the block, knocking it into the bin. The unloading rover updates the server to tell the delivery rover to begin its journey home, traversing through the best path in reverse order. Once back at the starting position, the delivery rover backs into place, ready for the next block.
The PIC32 communicates with a Wi-Fi RNXV interfaced over UART1. UART1 operates at a baud of 115,200. The UART instance is interrupt-driven and is capable of sending and receiving bytes in succession. The Wi-Fi module is programmed by connecting it to a USB adapter. A serial terminal can then be used to modify the settings of the Wi-Fi module. We used the PIC2 camera for obstacle and color detection. The PIC2 camera can be taught to recognize up to 7 different color signatures. It can communicate over UART, SPI, I2C, USB, or just plain analog or digital signals. We chose to use UART for the communication between the PIC32 and PIC2 camera. The camera PIC has 2 UART instances, one for the Wi-Fi and one for the Pixicam. The Pixicam uses RX and TX1, while the Wi-Fi uses RX and TX0. The rate at which the PIC requests data from the Pixicam is controlled by a software timer. The main thread of the camera PIC has an FSM to decode each received byte from the Pixicam. The PIC32 receives data from the Pixie camera, decodes it, and then sends the color, size, and position of up to 10 blocks to the server for pathfinding and obstacle detection purposes. Information is sent to the server by constructing an HTTP put request with the decoded block data as a JSON payload.
The rovers are comprised of a Zumo 2-tread rover that is a diff drive model, along with a chip kit motor shield connected to the PIC32. The motors are connected by a JST 6-pin connector with the motor shield, which connect them to 2 output compare channels for the DC motors, as well as 2 external interrupt pins for the encoders. Each external interrupt drives a counter. The motor API is designed to accept a command in the form of distance in centimeters and heading in radians. It will first execute a turn in place, followed by a forwards or backwards motion. A 2-tiered control system is used. First, the differential drive model kinematic equations shown on screen are used to convert the target forward and rotational velocities to left and right wheel speeds. These can then be integrated to obtain the total forward and rotational distances traveled. A top-level proportional distance controller calculates the desired wheel speeds based upon how far it is from the target position and feeds them into a PID controller for each tread. As each tread is an independent system, 2 PID controllers relating PWM signal to encoder feedback is used. It compares the expected speed, which is an encoder ticks per 50 millisecond period, to the feedback read from the encoder ISR. The PID controller uses proportional, integral, and derivative terms to calculate response based upon measured error. The proportional term is the basic controller, which increases the command when feedback is low and decreases the command when feedback is high. The integral term keeps track of how long error has existed and becomes more aggressive the larger the integral value becomes. Finally, the derivative term uses the current rate of change for the error to anticipate and eliminate future error. The following graphs show 3 commands executing back to back. First, the rover travels left 90 degrees and then forward 15 centimeters. Next, it turns right 90 degrees and travels backwards 15 centimeters before finally making a 180 degree turn and stopping. The first graph shows the integrated distance traveled in both linear, in blue, and rotational, in orange, forms. As can be seen in the graph, the controller will always handle the 2 types of moves separately. The second graph shows the expected encoder feedback per 50 millisecond time step versus the actual response. You can see how both motors ramp up to the desired speed before ramping back down shortly before hitting their target. The final graph shows the actual PWM commands sent to the left and right motors. You can see how they ramp up and then oscillate as they hit and attempt to keep the target speed. The graph also shows how the right side of the unloading rover was significantly weaker, hence why it constantly required a higher PWM command to hit the same speeds.
The robot arm is controlled using a PIC32 with an added motor shield. There are 4 output compare pins in pulse width modulation mode. Pulse width modulation is a method used to manipulate a digital signal's duty cycle. The duty cycle is a proportion of time a signal is asserted within a given period cycle. The servos use this method to determine the desired position. The PIC also has added external power from an AC-DC adapter to the motor shield. This is used to power the servo separate from the PIC. A Wi-Fi module is used for communication with Raspberry Pi server through UART. The robot arm is controlled with 2 threads, a network thread and a servo control thread. The network thread receives information from the Raspberry Pi server with the use of a JSON payload. This payload is parsed with Jasmine, an open source JSON parser. The network thread then constructs an order of commands that are sent to the servo control thread. Once these commands are started, the arm will go into an unavailable state in the Raspberry Pi server until the task is complete. The servo control thread receives a command and updates the PWM or pulse width modulation value of each servo based on the desired position. The speed at which the PWM values change is controlled by a software timer. This allows safer movement of the servos and prevents excessive current usage. Once a command is completed, a special character is sent back to the network thread, which notifies it to send the next command. Once all the commands are completed, the arm will return to an available state on the Raspberry Pi server. The arm is operated with the use of 4 servos. There are 3 MG90S servos. 2 control the movements of the arm and 1 controls the movements of the claw. They operate at 5 volts, have a pulse width of 400 to 2400 microseconds and a pulse cycle of 20 milliseconds. There is one MG996R servo that controls the direction of the arm is facing. It operates at 5 volts and has a pulse cycle of 20 milliseconds.
Raspberry Pi 3 runs a Flask server to handle HTTP requests from all of the PICs. A routing was created for each PIC32 microcontroller, this being the delivery and unloading rovers, the servo-powered robotic arm, and the top-mounted PIXI cam. The server uses an Apache server configured as a reverse proxy to forward simultaneous requests to our Python Flask server. This way, all PIC32 microcontrollers may send HTTP requests to the Raspberry Pi at the same time. A GUI was created to track the rover location and the obstacle locations in a grid format. We used tkinter and wrote it in Python. It uses the block size and position received from the camera pic to calculate how many grid spaces to take up on the GUI. It refreshes at regular intervals to ensure live obstacle and rover movement visuals. The best path as computed upon startup is shown on the map in blue. To find our way through the obstacles, an A-star pathfinding algorithm is employed in Python and called from the Flask server's backend code whenever a GET request to /mapsln is received. The result as coordinates is then returned from the request. The algorithm attempts to find the shortest path from a starting point to a known destination. To make a decision on where to go next, the approximate distance to the destination from the current location is recomputed on each iteration. Our solution computes the Euclidean distance to accomplish this. I'll go over the threads running on the delivery rover code. This begins with a network thread. This thread takes data from other threads through a single message queue and sends corresponding HTTP requests to the server. A specific struct is passed through this single queue. This helps achieve passing of data from multiple different areas, using a status and a source field to know where they came from. The Jasmine JSON parsing code looks for the JSON field names from an HTTP response and returns the corresponding data. Depending on which field is populated or present, a response is built and sent through the world state queue in such a way that the main navigation thread recognizes and takes action accordingly. The main navigation thread contains the movement logic conversion from coordinates to motor commands. A function to take the coordinates of the delivery rover's path must be converted to the format expected by the motor control's thread queue. This format expects a distance and a turn parameter in radians. This logic decides whether the rover needs to turn or just go straight in order to get to the next coordinate. This logic will send multiple commands in order to traverse a single coordinate if necessary, as in the case of diagonal movement. States determine whether the rover will traverse the course, return home, wait for loading, or wait for unloading. The rover has a few states which correspond to real-world activity: init, loading, moving, unloading, and returning. These states are sent every 600 milliseconds to the server as to update the other PICs on the delivery rover's location. When the delivery rover reaches the destination, it enters the unloading state. The unloading rover is periodically checking the server for the delivery rover state. When it sees it has entered the unloading state, it will commence unloading. Our design could use a few improvements and further development. Firstly, the communication between the delivery rover and the arm has an issue where the delivery rover leaves too early on the second run of the system. This could be resolved by adding another state to the arm rover in which the arm is moving. This would prevent the rover from arriving, checking the server, and seeing the same status it did that triggered it to leave the first time, preventing it from waiting. Secondly, the delivery rover tends to drift on successive straight moves. This could be corrected by utilizing some external force, such as the PIXI cam, to watch the rover and send it commands to correct drift. Lastly, we couldn't get right turns working on the delivery rover codebase. Matthew was able to get right turns to work great on his isolated testing code, but something went wrong when porting it to the delivery rover code. The cause is still yet to be determined. Unfortunately, while the overall system runs for multiple cycles, the block is only successfully delivered on the first run due to the bug mentioned earlier. Our design only works on the set playing space, being the white poster board. While the code seems stable, a Wi-Fi would occasionally flicker off and back on. Sometimes this would result in that PIC no longer pinging the server, resulting in the system halting before the next state. Thank you for watching. We hope you enjoyed our project video and found our work interesting.